Okay, let's just dive right in. Welcome to the deep dive. Today we're looking at a very specific and pretty unusual long-range forecast.
We are. It's an expert prognosis for severe winter weather across a huge area, Northern Eurasia, so Europe, Russia, the Caucasus.
And for a very specific window, right? November 30th to December 9th, 2025.
Exactly. And the executive summary here is, well, it's sobering. The overall risk is assessed as high moderate.
And some areas are even getting a high-risk designation.
That's right. And what's really getting attention is the lead time. I mean, we're looking at a high-impact forecast almost a full year out.
Which brings us to the big question, the one I know you're thinking. How on earth can anyone predict a major weather event that far in advance? I mean, my 10-day forecast is usually wrong by day 5.
Yeah, that's the fundamental challenge, right? The atmosphere is just chaotic. Your standard daily forecast, a deterministic one, it's really only reliable for maybe 7-10 days at the most.
So this is something else entirely. They aren't trying to say if it'll be snowing in Berlin on a specific Tuesday?
No, not at all. They're using a different method. This is a probabilistic subseasonal forecast.
So in plain English, what does that mean?
It means we're stepping back from the daily details. We're looking at the big, slow-moving drivers in the climate system. We're forecasting the probability of a certain weather regime taking hold, not the day-to-day weather.
Got it. Tracking the big waves, not every little ripple. And it seems like the models are seeing 2 of these big waves about to sync up.
Precisely. That's the aha moment here. First, we have very high confidence that a weak La Nina event will still be active in the Pacific. That's a huge, stable oceanic driver.
Okay, so that's the foundation.
Right, and then comes the trigger from above.
Yeah.
There are strong signals of an unusually early and major disruption of the polar vortex, a big stratospheric warming event.
So you have this stable ocean pattern and then this chaotic event in the upper atmosphere happening at the same time.
And that synchronization forces the atmosphere into a very specific, very stubborn pattern.
And that pattern is a protracted negative phase of the Arctic Oscillation, the AO, and the NAO.
Yes. And you can think of the AO and NAO as like the belt that holds the jet stream in place. When it goes strongly negative, that belt loosens.
Yeah.
And the whole thing just sags southward and becomes sluggish.
So a sluggish jet stream dropping south over Europe. What does that actually do?
It does 2 very dangerous things. First, it just opens the door for deep, bitterly cold air from Siberia to spill westward into Europe.
The so-called beast from the east.
Exactly. But second, and this is crucial, that southerly jet stream track picks up a ton of moisture from a potentially warmer than average Atlantic and Mediterranean.
And it directs all that moisture right into the cold air.
And that's the clash. That's the setup for what we call explosive cyclogenesis.
Which is basically a storm that intensifies incredibly quickly.
Incredibly quickly. And when that happens at the freezing line, you get the absolute worst case outcomes. Widespread, crippling freezing rain, intense blizzards, things that take down power grids.
So let's talk about the hotspots. European Russia, Eastern Europe, that seems like ground zero for this collision.
It is. But the other high-risk zone is the Caucasus region.
Why there specifically?
Because that southern storm track slams directly into the mountains. That forces the air upwards, we call orographic lift, and that squeezes out just massive amounts of snow.
And I'm guessing it's not just about snow. You're probably looking at a cascading hazard risk.
You are. You pile that much snow onto already unstable glaciers, a known effect of climate change there, and you dramatically increase the risk for avalanches, for landslides, for mudslides.
Which brings up the big paradox. We're talking about a historic cold outbreak. So where does long-term global warming fit into this picture?
It's the critical amplifier. I mean, it comes down to a law of physics, the Clausius-Clapeyron equation.
Which basically says warmer air holds more water vapor.
A lot more. So when this rare natural cold pattern happens today, in our warmer world, the storms it produces are supercharged with moisture. The precipitation they drop, whether it's snow or freezing rain, is far more intense than the same pattern would have produced 50 or 100 years ago.
So the warming makes the cold event worse.
It makes the impacts of the cold event much, much worse.
Okay, so to sum this up, what we're seeing is a period where strong natural variability, the La Nina and the polar vortex acting together, it temporarily punches through the background warming trend.
Exactly. And it leaves us with a final kind of provocative thought for you to consider. When one of these rare natural cold patterns finally occurs in a world that's already loaded with extra moisture from warming, Does the sheer severity of that storm mean that, paradoxically, our biggest short-term climate risks actually come from the cold? It's that interaction we have to start planning for.